My name is Kevin Rosas, and this presentation covers the Physics 2211 Lab 3. This lab investigates the gravitational motion using computational models. In Part 1, we estimate that the mass of the black hole by analyzing the orbit of a star. In Part 2, we simulate a planet, moon, and spaceship system to determine a velocity that allows the spaceship to travel through the system without crashing. So the main idea of this lab is to connect motion with the forces. In Newton's second law tells us that the rate of change in momentum equals the net force acting on an object. By measuring how the star's momentum changes over time, we can determine the gravitational forces acting on it and calculate the mass of the black hole. Three main physics principles were used. Newton's second law, which relates forces to the rate of change of momentum. Momentum is defined as mass times velocity. The gravitational force equation describes how two masses attract each other. And combining these equations, we can solve for the unknown mass of the black hole, which is given here on the right-hand side. For the system and surroundings, in Part 1, the system is a star, and the surrounding objects is the black hole producing the gravitational force on the star. For Part 2, the system includes the moon and the spaceship, while the other massive bodies influence their motions. And so here is my code for Part 1, and so the analysis was performed using VPython computational models. The program calculates velocities from the position data and then determines the star's momentum. From this, it calculates the rate of change in momentum and uses Newton's second law to determine the net force. The force is separated into parallel and perpendicular components that changes the speed and direction of the star's motion. And in terms of my results for this lab, for Part 1, this image shows the simulated orbit of the star around the black hole. And because the orbit is elliptical, the gravitational force changes as the star moves closer or farther from the black hole. The program calculates the black hole's mass at multiple points and then later averages all of the masses to get the final result. And so the calculated mass that I got was approximately 1.5 times 10 to the 34 kilograms. And so this result confirms Newton's second law. The change in momentum we observe from the star's motion corresponds directly to the gravitational forces acting on it. The perpendicular component of the force curves the orbit while the parallel component changes its speed. In Part 2, the simulation models a planet, moon, and a spaceship. The moon orbits a planet, while the spaceship experiences gravitational forces from both objects. The program calculates these forces and then updates the motion of each object over time. And that's what we see here. And in terms of my results, this image shows the path of the spaceship, and through trial and error, an initial velocity of about 0,1350, 0 produced a trajectory that allowed the spaceship to pass through the system without crashing. And so if we modeled the entire system, including the black hole, star, planet, and moon, we would need to calculate the gravitational forces between each pair of objects. And in terms of which forces would dominate, the largest interactions would dominate the motion, particularly the black hole, star, and the planet-moon interactions. And in conclusion, this lab demonstrates how computational models can be used to analyze gravitational systems, and by applying Newton's second law to the motion of a star, we can estimate the mass of a black hole. We then modeled a multi-body gravitational system and determined a spaceship's trajectory influenced by multiple gravitational forces. Limitations of this model includes numerical approximations and the assumption that only gravitational forces act on the object.